If you have ever stood outside on a clear night and listened, really listened, not to the wind or the distant road, but to the sky itself, you may have noticed something strange about it. The stars do not hum. The galaxy does not whisper. For all the fire and violence visible in every direction, the cosmos offers us nothing in return when we call out to it. No voice, no signal, no acknowledgement that we are here. Physicists have a name for this. They call it the Great Silence. And the strangest thing about the Great Silence is not that it exists, it is that it shouldn't. The paradox was first sharpened into a single sentence in 1950 at a lunch in Los Alamos, New Mexico. The physicist Enrico Fermi was walking to the cafeteria with 3 colleagues, discussing a recent cartoon in the New Yorker that joked about flying saucers. The conversation drifted toward the question of whether interstellar travel was physically possible. They worked through the numbers casually, the way physicists sometimes do over food. Speeds, distances, timescales. And then, somewhere between sitting down and picking up his fork, Fermi is said to have asked a question that has never really been answered. He asked, "But where is everybody?" It was not a rhetorical question, it was a real one. And the reason it has haunted astronomers for 75 years is not that it is strange. It is that, the longer you sit with the arithmetic behind it, the more it begins to feel like an accusation. Because the Milky Way is old. Our galaxy contains somewhere between 100 billion and 400 billion stars. The most recent estimates lean toward the higher end. A significant fraction of those stars, roughly 1 in 5, according to data from the Kepler Space Telescope, host at least one planet in what astronomers call the habitable zone, the narrow band of orbital distance where liquid water can exist on a rocky surface. If you do the multiplication gently, without reaching for the most optimistic numbers, you are still left with something in the range of tens of billions of potentially habitable worlds in this galaxy alone. And the Milky Way has been here for roughly 13.6 billion years. That is the number that should trouble you. Not the size of the galaxy, the age of it. Life on Earth appeared, as far as we can tell, within the first billion years or so of our planet's existence. Not 5 billion years in, not after some long, grinding delay. Almost as soon as the crust cooled enough to hold oceans, something in those oceans began to replicate itself. Whatever the recipe is for turning chemistry into biology, it seems to work quickly, at least under the right conditions. And there is no reason, none that we have yet been able to find, to believe that the conditions on Earth are particularly rare. So consider what this means. If even a small fraction of those tens of billions of habitable worlds produced life, and if even a small fraction of those living worlds produced intelligence, and if even a small fraction of those intelligent species developed the capacity to build radio transmitters or spacecraft, then the galaxy should by now be full of signals, full of probes, full of evidence. A civilization only slightly more advanced than ours, moving at speeds we already know to be physically achievable. Not the speed of light, nothing exotic, just a fraction of 1% of it, could, in principle, spread across the entire galaxy in somewhere between 10 million and 50 million years. That sounds long, but remember, the galaxy is 13.6 billion years old. 10 million years is less than 1/10 of 1% of that age, which means that if a single technological civilization had arisen anywhere in the Milky Way at any point in the last 100 million years, they should already be here. Their fingerprints should be on every star system we look at. Their probes should be in our asteroid belt. Their signals should be bleeding through our radio telescopes every night. Instead, there is nothing. We have been listening for almost 70 years. The sky, to our instruments, is empty. This is the Fermi paradox. And if you are lying awake tonight, unable to sleep, I think it is worth sitting with for a little while. Not because it is frightening, but because the silence is telling us something, and we have not yet learned how to hear it. I should say, before we go further, if the slow, quiet nights on this channel are useful to you, you can follow along by subscribing. That is all. No urgency, just if it helps. Now, let us begin properly. There are, broadly speaking, 3 kinds of answer to Fermi's question. The first kind says that we are alone, that something about the origin of life, or the emergence of intelligence, or the survival of technological civilizations is far rarer than we have been assuming. The second kind says that we are not alone, but that the universe is much larger and stranger than our detection methods can reach, and so the silence is an illusion of our limitations. The third kind, and this is the one that keeps some astronomers up at night, says that the silence is real and that it is a warning. We will walk through all 3. But I want to begin with a small, specific object, a thing you can hold in your mind. Because the paradox becomes easier to feel when you anchor it to something concrete. In 1977, a probe was launched from Cape Canaveral and given the name Voyager 1. It was a modest machine by modern standards, about 720 kilograms, a gold-plated record on its side containing sounds from Earth, whale songs, greetings in 55 languages, a recording of a human heartbeat. Voyager 1 was not designed to find alien civilizations. It was designed to photograph the outer planets and then, having finished its primary mission, to drift. It is still drifting now, nearly 50 years later. As I am speaking to you, Voyager 1 is somewhere in the vicinity of 165 astronomical units from the Sun. That means it is roughly 165 times farther from the Sun than the Earth is. A signal traveling at the speed of light takes about 23 hours to reach it. If you sent a radio command to Voyager right now, and it answered immediately, you would not hear the reply until tomorrow night. And yet, and this is what I want you to feel, Voyager 1 has not even left the solar neighborhood, not even close. It crossed what is called the heliopause, the boundary where the Sun's particle wind gives way to the interstellar medium in 2012. In that sense, it is in interstellar space. But it is still enormously far from any other star. At its current speed, it would take Voyager approximately 74,000 years to reach the nearest star to our Sun, which is Proxima Centauri, about 4.2 light-years away. And Proxima Centauri is not going to be in the same place when Voyager arrives. Nothing in this galaxy stays still. So here is the small image to hold on to. A human-made object, the farthest one we have ever built, has spent nearly 50 years flying outward at more than 60,000 kilometers an hour, and it has not yet crossed 1,000th of the distance to the nearest neighboring star. The galaxy is large in a way that the human mind is not equipped for. And still, the paradox insists that this distance should not be enough to protect us from contact. Because the galaxy is not just large, it is old. And time, given enough of it, collapses every distance. Think of it this way. Imagine a civilization that emerged on some unremarkable rocky planet around some unremarkable yellow star, 1 billion years before Earth's first single-celled organism.
1 billion years is a long time. It is roughly the span between the formation of our oceans and the appearance of the first recognizable animals. If that civilization survived even a fraction of that billion years, if they lasted, say, 10 million years as a spacefaring species, then by the time the first fish crawled onto the land of our young Earth, their descendants would have already had every opportunity to seed the galaxy with self-replicating probes, to establish colonies on every reachable world, to leave monuments and transmitters and slow, patient artifacts in every solar system. They would be here, in our sky, in our soil, in our radio signals, and they are not. There is a concept physicists sometimes use to describe this. It is called a Bracewell probe, after the astronomer Ronald Bracewell, who proposed it in the early 1960s. The idea is simple. A civilization that wants to make contact across vast distances does not need to send ships. It only needs to send machines. Small, self-replicating machines that drift from star to star, using the raw material of each new system to build copies of themselves. Each generation doubles, then doubles again. The expansion is exponential. Run the arithmetic out, even with very conservative assumptions, slow probes, long gestation times, cautious replication, and the math still produces the same unsettling result. A single civilization launching a single probe could colonize the entire Milky Way in a window of time that is, on the cosmic scale, almost instantaneous. 10 million years, maybe 50 million at the slowest, a blink. And yet in our solar system, which has been here for 4.5 billion years, which has hosted life for more than 3.5 billion of those years, we have never found a probe. We have looked. We are looking now in the asteroid belt, at the Trojan points, in lunar orbit. There is nothing. There is no message, no monolith, no trace.
This is what the astronomer Michael Hart pointed out in a famous paper published in 1975, 25 years after Fermi's lunchtime question. Hart argued that the absence of extraterrestrials on Earth, not in the sky, on Earth, was itself the evidence. Not the lack of radio signals, the lack of visitors. Because if any civilization had ever arisen in our galaxy and decided to expand, they would have arrived here long before we did, and they would still be here. Because once a species crosses interstellar distances, there is no reason for them to ever leave. The silence, Hart said, is not neutral. It is informational. It is telling us something about the fate of civilizations. And here, I think, is where the paradox begins to change shape, because up to this point, we have been talking about numbers, about probabilities, timescales, galactic arithmetic. But the silence is not a number. The silence is a fact we live inside. Every night you lie awake and look up at the ceiling, and somewhere above that ceiling, past the roof and the atmosphere and the thin blue membrane of the day sky, there is a galaxy with 400 billion stars in it, and no one we have yet been able to detect is trying to reach us. Sit with that for a moment. It is now, I think, very late. The hour when the streetlights outside look different than they did at midnight, colder somehow, more like the light of another world. If you are awake at one of the strange hours. These are good hours for thinking about distances. Let me tell you about the second way astronomers have tried to listen. In 1960, at the National Radio Astronomy Observatory in Greenbank, West Virginia, a young astronomer named Frank Drake pointed an 85-foot radio telescope at two nearby stars, Tau Ceti and Epsilon Eridani, and listened for a few hundred hours. He was searching for narrowband radio signals, the kind of emission that does not occur naturally, the kind that can only come from a technology. He called the effort Project Ozma, after the princess in the Oz books who lived in a distant and imaginary land. He found nothing. That was 66 years ago. Since then, the effort that Drake began has continued, on and off, sometimes well-funded and sometimes starved of money, under various names and organizations, but always with the same underlying question at its center. The effort is called SETI, the search for extraterrestrial intelligence. Over 6 decades, SETI researchers have listened to thousands of nearby stars, across a wide range of radio frequencies, using instruments that have grown steadily more sensitive. In 2015, the Russian-American philanthropist Yuri Milner funded a new initiative called Breakthrough Listen, which has scanned roughly 1 million nearby stars and about 100 nearby galaxies. The total volume of the galaxy we have carefully examined across all this effort remains small. Critics of SETI sometimes compare it to dipping a drinking glass into the ocean, pulling it up, finding it empty of fish, and concluding that the ocean contains no fish. This is a fair criticism. The sky is enormous, and our ears are small, and we have been listening for a historical eye blink. But even accounting for this, the result so far is a quiet that presses against the eardrums. The radio sky, to the precision we have been able to measure it, shows no sign of intentional communication. We have picked up 1 or 2 signals over the decades that briefly excited researchers. The so-called WOW signal detected at Ohio State in 1977 being the most famous. But every such case has either never repeated or has been traced to a natural or terrestrial source. Nothing has held up. Nothing has been confirmed. Which brings us back to the question,
Why? There are a handful of serious answers to Fermi's question, and I want to walk you through them slowly, because each one has a different shape, and each one changes the feeling of the sky when you look up at it. The first answer, and the oldest, is that life itself is rare. Not intelligent life, life of any kind. The idea is that the step from non-living chemistry to self-replicating biology, the moment when a collection of molecules first folded into a pattern that could make copies of itself, may be so improbable that it only happens once in a very long while, on a very small number of worlds, perhaps once per galaxy, perhaps once per galactic cluster, perhaps, in the observable universe, only here. This is sometimes called the rare life hypothesis, and it has a certain quiet appeal. It preserves our intuitions about how physics and chemistry work, while explaining the silence as a simple matter of isolation. We are not alone because intelligent civilizations are failing. We are alone because the door from chemistry to biology is almost always locked. The trouble with this answer is that we have only one example of life in the universe, our own, and it is a very quick one. As I mentioned earlier, life on Earth appeared within the first billion years of the planet's existence, possibly much earlier. The chemistry seems to have found the pattern almost as soon as the conditions allowed for it. If it were truly rare, we might expect to have had to wait. Instead, the fossil record suggests that life was waiting for the oceans, not the other way around. Still, one data point is not a sample. It is possible that we are the lucky planet, that the universe, for all its billions of years and its trillions of worlds, produced biology exactly once, here, and that everything we call a night sky is dark for this simple reason. That is the first answer. The second answer accepts that simple life is common, but argues that the jump to complex, multicellular, intelligent life is what is rare. This is sometimes called the rare earth hypothesis, developed in a book of the same name by the paleontologist Peter Ward and the astronomer Donald Brownlee in the year 2000. The argument, roughly,
is that even if microbes are common across the galaxy, the specific chain of improbable events that led from a single cell to a thinking animal, the evolution of the eukaryotic cell, the rise of sexual reproduction, the Cambrian explosion, the long survival of a stable climate, the timely extinction of the dinosaurs. All of these may be contingencies that happen to line up for us, and that almost never line up elsewhere. Under this view, the universe is full of life. Oceans beneath the ice of Europa, lichens clinging to the rocks of Mars, bacterial mats drifting in the sulfur clouds of Venus. But almost none of it ever climbs up toward anything we would recognize as mind. The galaxy is populated. It simply has no one to speak with. There is something gentle about this answer, if you let yourself feel it. Not a dead universe, a living one, just a quiet one. A universe where thought is the rarest thing, and we are, as far as we can tell, one of the few places where matter has learned to ask questions about itself. The third answer goes further. It says that the rare step is not life, and not even complex life, but the narrow window between becoming technological and becoming extinct. This is sometimes called the Great Filter. The term was coined by the economist Robin Hanson in the mid-1990s, and it refers to the idea that somewhere along the long path from lifeless matter to galaxy-spanning civilization, there is a step that almost nothing gets past, a bottleneck, a filter. And the question that some astronomers find genuinely frightening, is whether the filter is behind us or still ahead.
If the filter is behind us, we are lucky. We have already passed the hardest step. Perhaps it was the emergence of life itself. Perhaps it was the leap from single-celled to multicellular. Perhaps it was the development of a large, metabolically expensive brain. Whatever it was, we are on the far side of it now, and the galaxy is silent because very few others ever made it this far. If the filter is ahead of us, the picture is different. Then, the silence is telling us something about the future rather than the past. It is telling us that civilizations, once they reach roughly the stage we are at now, industrial, nuclear, networked, capable of altering their own planet's climate, tend not to survive very long. Not long enough, at least, to be detected. They build their radio telescopes and their weapons at roughly the same time, and the weapons tend to win. Or the climate collapses. Or some technology we have not yet invented turns out to be the thing that quietly ends us. Under this view, every planet in the galaxy that has ever produced intelligence has also, eventually, produced its own end. And we are not an exception. We are simply the latest species to arrive at the filter and look through it and wonder which side we are on. I want to say something about this because it sounds bleak. It is not, necessarily. The Great Filter is a hypothesis, not a prediction. It is one possible interpretation of a silence that could have many causes. What it offers is a useful thought experiment, a way of noticing that our choices now, in this century, might matter in a way that extends far beyond ourselves. The silence may or may not be a warning, but it gives us permission to treat our own survival as something worth attending to, not out of fear, out of care. There is a slightly different shape to this answer that I think is worth pausing on. Some astronomers have suggested that the filter may not be a single step, but a long, sustained drift.
That civilizations do not explode or collapse. They simply fade. They turn inward. They build worlds inside their computers and lose interest in building ships. They become, in the words of one astronomer, small and quiet and content. And the galaxy fills up with their silence because they are no longer trying to leave footprints. If that is true, then the sky is not empty. It is merely polite, filled with minds that have decided they do not need to shout. I find this idea strangely moving. It suggests a maturity we have not yet reached, a species that does not expand for the sake of expanding, that does not conquer stars the way it once conquered continents, that looks up, one night, at its own sky full of civilizations it cannot hear, and decides to let them be. The hour is getting later now. I can feel it in the way the words are settling. If you are still awake, that is all right. There is no rush to any of this. The galaxy is not going anywhere. There is a fourth family of answers, and this one is harder to describe, because it asks us to question the assumption that we would know contact if we saw it. We search for radio signals. We scan for laser pulses. We listen on frequencies we have decided, based on our own physics, would be the natural choice for a civilization trying to reach us. But our physics is about 1.5 centuries old. Our radio telescopes are younger than that. If there are civilizations in this galaxy that have been technological for 1 million years, 10 million years, 100 million years, and the numbers suggest some of them should be, then their methods of communication, if they are still communicating at all, may bear no resemblance to ours. They may use neutrinos, gravitational waves, modulated pulsars, methods we have not yet imagined. They may encode information in patterns so subtle and so slow that we would need to watch a single star for 10,000 years to notice the signal was there.
Our civilization, measured against such scales, has been paying attention for less than a human lifetime. We are an infant standing in a concert hall with our ears covered, wondering why we cannot hear the orchestra. There is a related possibility, sometimes called the zoo hypothesis, first proposed by the MIT astronomer John Ball in 1973. Ball suggested that advanced civilizations might be aware of us and might have deliberately chosen not to reveal themselves. Perhaps they are observing. Perhaps there is a galactic convention, an informal agreement, that young species should be left alone to develop without interference. Perhaps we are a kind of nature preserve, watched from a distance, allowed to grow. This hypothesis is, by its nature, untestable. That is one of the reasons it is not taken as seriously as some of the others. A theory that predicts we will never see evidence is a theory that can never be confirmed. But I mention it because it illustrates a deeper point, that our definition of silence assumes we know what contact would look like, and we do not. We are using our own language to ask a question of something that may not speak it. Let me tell you about a particular night on a particular mountain, because sometimes it helps to ground these ideas in something specific. There is a radio telescope in West Virginia, in a valley called Green Bank, in a region of the United States designated as the National Radio Quiet Zone. Within this zone, the use of most wireless technology is restricted. Cell phones do not work. Wi-Fi is regulated. The surrounding mountains act as a natural shield against radio noise from the outside world, and the result is a kind of silence that most of us have never experienced. A silence not only of sound, but of the electromagnetic spectrum itself. At Green Bank, a sensitive instrument can listen outward without the background chatter of microwave ovens and garage door openers and passing satellites. On a clear winter night at Green Bank, the telescope points at some distant star, and the data is recorded, and the researchers go home. In the morning, they look at the spectra. They look for anomalies, patterns that should not be there, narrow lines at frequencies that no natural process produces. Almost always, they find nothing. Occasionally, they find something that looks like something, A spike in the data, a narrow line at a suspicious frequency. The pulse rate quickens. The signal is examined. It is almost always, eventually, traced to a satellite, a microwave leak, a nearby transmitter that briefly escaped the quiet zone's control. The excitement fades. The notebook is closed. This is what the search for alien civilizations actually looks like. Not dramatic, not cinematic. A small number of tired humans in a few buildings scattered around the world, reading columns of numbers at 3 in the morning, trying to decide whether a brief fluctuation in a radio receiver is an artifact of the instrument or a message from a world around a star whose light left it long before our species knew how to write. 66 years of this, and we are, so far, still alone. I want to return to Voyager 1 for a moment because I think the image is important. As Voyager drifts outward, its transmitter is powered by a small radioactive source, a piece of plutonium that is slowly, steadily decaying. The signal it sends back to Earth has grown weaker every year. By the mid-1990s, it was already fainter than the background noise of the galaxy itself, and only careful signal processing allowed us to pick it out. Sometime in the late 2020s, the plutonium will no longer produce enough power to run the instruments. The final signals will be sent. Voyager will go quiet. After that, it will still be there. It will still be moving. It will still be carrying its golden record, its whale songs and heartbeats and greetings in 55 languages.
But it will be silent. It will drift through the dark between the stars at roughly 60,000 kilometers an hour, which sounds fast and is not fast. And in about 40,000 years, it will pass within roughly 1.5 light years of a star called Gliese 445. Not close. Not close enough for anyone there to notice. Just nearby, in a galactic sense. Then onward. Voyager will outlive the sun. When our star finally swells into a red giant and consumes the inner planets, some 5 billion years from now, Voyager will already be far beyond its reach, still carrying the record, still falling through the dark. It will likely outlive the Earth. It may outlive the human species by a very long time. Perhaps, one day, something will find it. Perhaps nothing will. This is what we have sent into the silence. A small machine with a message. A kind of letter in a bottle thrown into an ocean so large that the word ocean does not begin to describe it. Now think about this. If we, with a civilization less than a century old in terms of spaceflight, have already launched a Voyager, then every civilization that has ever existed in our galaxy and lasted even slightly longer than we have should have launched thousands, tens of thousands. Every solar system in the Milky Way should have at least one such artifact drifting through it, quiet, dark, patient, waiting to be noticed. We have looked. There is nothing. The silence, in other words, is not just the silence of radio waves. It is the silence of objects, the silence of visitors, the silence of every physical trace that an older civilization might have left behind. The galaxy is not only quiet, it is clean. And this, for some astronomers, is the most disturbing version of the paradox. Because radio signals fade, signals can be missed. Signals require deliberate transmission. But probes do not fade. Probes do not need to be aimed. A probe sent 100 million years ago and forgotten by its makers should still be here, in our solar system, on our moon, in the debris of our asteroid belt. The fact that we have not found one means either that no such probes have ever been sent, or that they are so well hidden that we would not know them if we looked at them directly. Both possibilities are strange. Neither is comfortable. I would like to tell you something here that is true, and that I have been thinking about for a long time. The strangeness of this silence
does not frighten me. It used to. When I first started reading about the Fermi paradox many years ago, there were nights when I would lie awake and feel the weight of it, the sense that something was missing from the universe, that we had been expecting company and had arrived at an empty house. But slowly, over time, that feeling changed. Because the silence is not personal. The universe is not withholding. It is not playing a trick on us. It is simply large, and we are simply new. And whatever the reason for the quiet, it is not a reason that requires us to suffer. The silence is not an insult. It is a condition. Like the cold of space, or the speed of light, or the slow drift of the continents. Something to live inside, not something to fight. There is a small image I return to sometimes, late at night, when the house is dark, and the street lights through the curtains are the only light in the room. I think of a single window, very far away, somewhere across an impossible distance, with a light on inside it. Maybe there is someone there, maybe there is no one. But the light is there, and I am here, and the distance between us is so vast that we will never meet. And there is something in that image, something about the simple fact of 2 points of light, burning in their separate rooms, unaware of each other but real, that I find, I do not know how else to say it, steadying. We are perhaps that kind of light.
Burning in our own window, unseen by whoever might be across the dark. Not lost, just far. Let me speak now about time, because I think the paradox cannot be fully felt without it. The human species, as a recognizable biological form, is about 300,000 years old. Our written history covers roughly the last 5,000 of those years. Our ability to send radio signals into space began a little more than 100 years ago. Our dedicated search for extraterrestrial signals is about 66 years old. Put together, the window during which we have been technologically visible to any other civilization is, on the timescale of the galaxy, essentially zero. If another civilization were transmitting to us from 1,000 light-years away, their signal would have been sent 1,000 years ago. When their technicians pressed the button, our ancestors were living in a world without clocks, without printing presses, without telescopes. When their signal arrived here, we would need to be listening at exactly the right frequency, with exactly the right equipment, in exactly the right moment. Miss by a decade, and the message passes through the solar system unheard, continues outward, is gone. This is why some researchers have argued that our failure to detect signals tells us relatively little. The problem is not just the size of the galaxy. It is the size of the galaxy in time. Two civilizations that are separated by even a few thousand years of development may never overlap in a detectable way. They may rise and fall in different millennia. They may both have sent signals and missed each other entirely, and died without ever knowing the other existed. This, to me, is one of the saddest versions of the paradox. Not that we are alone, but that we are not alone, and that the not aloneness is unreachable. That somewhere out there, across the river of time as much as the river of space, there have been others, and the currents between us were too strong. And we simply missed. A light in a window, briefly lit, briefly watched, and then passed. The search continues. New methods are being tried. The Breakthrough Listen project, which I mentioned earlier, is now scanning at wavelengths and sensitivities unavailable to Drake in 1960. The James Webb Space Telescope, launched in 2021, is for the first time able to analyze the atmospheres of distant exoplanets and look for chemical signatures that might suggest life. Not intelligence, but life. Methane in combination with oxygen, for example, would be difficult to explain without biology. If we find such a signature, we will not have found alien civilizations, but we will have found alien biospheres,
And even that would be, in the quiet way these things are, a revolution. But we have not found them yet. The atmospheres we have measured so far look, to the precision we can reach, unremarkable. Which does not mean they are lifeless, only that whatever life they may hold, if any, is not the kind that rearranges the chemistry of a whole planet in a way our instruments can detect from 50 or 100 light-years away. The search goes on. There is one more answer to Fermi's question that I want to speak about. It is, in some ways, the strangest of them, and I have saved it for now because it requires a kind of stillness to hear properly. Some astronomers have suggested that the silence is neither the silence of empty space nor the silence of failed civilizations. It is, instead, the silence of something deliberate, something chosen. The idea is called, informally, the dark forest hypothesis, though the concept predates its popularization in fiction and has been discussed in various forms by serious researchers for decades. The argument runs roughly like this. In a galaxy where any civilization could, in principle, destroy any other civilization across interstellar distances, using weapons we can already imagine in outline, such as relativistic projectiles or directed energy devices, the safest strategy for any intelligent species might be to stay quiet, to listen without speaking, to hide. Under this view, the galaxy is not empty, it is full. Full of civilizations that have all, independently, arrived at the same conclusion, that transmitting one's position to the void is an act of enormous and unnecessary risk, and so they do not transmit. They do not build great beacons. They do not send probes with gold-plated records of their music and their children's voices. They stay dark. They watch. They wait. And the young, loud civilizations, the ones still broadcasting their television signals in every direction, still sending out messages on purpose, are the ones that do not last. I want to be careful here. The dark forest hypothesis is, at present, speculative. There is no direct evidence for it. It relies on assumptions about the behavior of civilizations we have never observed, and those assumptions may be entirely wrong. A civilization millions of years older than ours may be unrecognizably kind. It may be so secure in its power that no threat we could pose would matter. It may have no interest in us at all. But the hypothesis is worth mentioning for a single reason. It reminds us that silence can be a choice, that the absence of contact is not always the same as the absence of life. The sky above us, right now, might be full of attention that we have no way of detecting. Not hostile, not benevolent, simply careful. If that is true, then the light in the window is not unwitnessed. It is watched, quietly, from a great distance, by someone who has decided not to knock. I find, when I sit with this idea, that I am not frightened by it. I am not sure why.
Perhaps because the same carefulness that might keep a civilization silent is the same carefulness we ourselves might learn to practice, in time. Not as a tactic, as a kind of manners. Let me move now toward something broader, because I think the paradox, in the end, opens onto something larger than itself. The silence of the sky is often discussed as if it were a problem, a puzzle to be solved, a mystery that demands a resolution. And it is, in a scientific sense, exactly that. But the silence is also a fact about our condition. Whatever the reason for it, we live in a universe in which, so far, no one has answered. Not the oceans of Europa, not the dust of Mars, not the countless stars we have scanned, not the atmospheres of the exoplanets we have measured. The reply to every call we have made has been the same: no reply. And we have to live inside that fact.
We have to figure out what kind of species we are going to be, knowing what we know. This, I think, is where the paradox stops being an astronomical problem and starts being a human one. If we are alone in this galaxy, truly alone, the only ones who have made it this far, then we are carrying something very rare. The only instance of self-aware matter in a volume of space larger than the mind can hold. That is not a reason for pride. Rarity is not the same as worth, but it is, at the very least, a reason for care, for treating this strange, unlikely thing we have become as something worth continuing. If we are not alone, but simply unable to hear, then the silence is an invitation to patience, to improving our instruments, to building better receivers and longer-running observatories, and the kind of civilization-scale infrastructure that might let us hear a whisper from 1,000 light-years away. We are, in that case, a young species standing at the edge of a conversation we cannot yet join, and it is worth staying in the room. If the filter is ahead of us, then the silence is a gentle warning.
Not a threat, a suggestion that whatever our ancestors survived to bring us this far, the hardest part may still be coming, and that we should be thoughtful, in this century and the next, about the choices we make, about nuclear weapons, about the climate, about the technologies we have not yet invented but will. The silence does not say that we will fail. It says that many before us may have, and that it is worth not being another. And if the silence is chosen, if there are elders out there who have decided not to speak, then we are, in some sense, still in our childhood, still being left alone to grow, still learning in the quiet what kind of species we want to become before we are ready to meet anyone at all. Any of these could be true. We do not know. And one of the deeper lessons of the paradox is that we may not know for a very long time, perhaps for longer than our civilization will last, perhaps, in some sense, forever. But the question remains. And it is, I think, a good question to hold. The hour is very late now. I can hear it in the quality of the silence. Sometime between 3 and 4 in the morning, the world acquires a particular kind of stillness, not the stillness of peace, but the stillness of attention, the sense that everything is listening to something. That is the hour the paradox belongs to. Not the noisy hours of the day, when the sky is bright and the questions feel abstract. The quiet hour, when the light above your ceiling fades into the great dark beyond it, and you can feel, for a moment, how thin the membrane between your room and the universe really is. We live our lives, most of the time, as if the sky were a ceiling, a painted surface, a backdrop. We forget that it is, in fact, a window, that above us always is the rest of everything, that the nearest star to our own, not counting the sun, is a little more than 4 light-years away, and that the next one after that is another few light-years beyond. That if we could travel in a straight line upward forever, we would pass through our galaxy and out into the halo of stars that surrounds it, and then out into the intergalactic dark, where the next nearest large galaxy, Andromeda, is 2.5 million light-years away. And beyond that, other galaxies. And beyond those, others. And the sky, every inch of it, is full of them. All of them quiet. All of them, so far, not speaking. There is something strange about being the kind of creature that can hold this in mind. The universe, as far as we can tell, produced a small and temporary arrangement of atoms on a small and temporary planet. that happen to develop the capacity to ask where everyone else is. That question has never, as far as we know, been asked by anything else in this galaxy. The asking is, itself, a new thing. A very new thing. 300,000 years old, and the asking only a few thousand of those. A brief candle in the long dark. And maybe that is, in the end, the right way to hold the paradox. Not as a problem, as a privilege. We are here, for a little while, in a universe we can barely see the edges of. We can ask where everyone else is. We can listen for an answer. We can build telescopes and probes and dreams of other minds. We can fail to find them and continue looking anyway. That is a good thing to be doing, whether or not anyone else is out there. The search does not require an answer to be worthwhile. I want to leave you with one more thought, and then I will let the rest of the night belong to you. The stars we see in the sky, the ones visible to the naked eye on a clear night, are almost all within a few thousand light years of us. A few thousand light years, in a galaxy 100,000 light years across. We are seeing, effectively, our neighborhood. The stars a little further in, a little further out. A tiny handful of the hundreds of billions that make up the Milky Way.
The rest of our galaxy, most of it, the vast majority, is invisible to us without instruments. Hidden behind dust lanes, behind distance, behind the simple limits of the human eye. And beyond our galaxy, there are, by the latest estimates, somewhere in the range of 2 trillion other galaxies in the observable universe. 2 trillion. A number so large that our language is not built for it. Each one of those galaxies contains, on average, somewhere between tens of billions and hundreds of billions of stars. Each of those stars is, on average, orbited by planets. Some fraction of those planets are rocky. Some fraction of the rocky ones are in the habitable zones of their stars. The arithmetic is staggering. Even under the most pessimistic assumptions, the number of potentially habitable worlds in the observable universe is so large that the human mind simply refuses to hold it. It rounds off to infinity. It becomes a symbol rather than a quantity. And somewhere in that vastness, if not in our galaxy, then in the next, or in some galaxy we will never be able to reach because the expansion of space is carrying it away from us faster than light can cross the gap. Somewhere, it seems very hard to believe that there is not, at least, someone else. We will almost certainly never meet them. The distances are too great. The timescales are too long. Space itself is expanding, and the galaxies that are not gravitationally bound to our own are drifting outward, forever, at speeds that will eventually place them beyond any possibility of contact. Whatever minds exist in those distant places are, for us, unreachable. Not because of any failure of technology, because of the shape of the universe. And yet they may be there, looking up at their own sky on their own late nights, asking their own version of Fermi's question, getting their own kind of silence in return. This is, I think, the deepest answer to the paradox. Not that we are alone, not that we are accompanied, but that the universe is structured in such a way that even if it is full of minds, each of those minds must largely find its own meaning in its own small corner, without much help from the others. We are, each of us, our own little light in our own little window, doing what we can with what we have, watching a sky that may or may not be watching back. It is enough, I think,
to be one of the lights, to know that there might be others, to fall asleep when sleep finally comes, with that thought held gently in the mind. The galaxy will turn tonight and tomorrow and for billions of years after we are gone. The stars will burn until they do not. New stars will form from the ashes. Planets will cool, oceans will fill. Chemistry may or may not fold into biology on shores we will never see. Somewhere, on one of those worlds perhaps, something will look up at its own night sky and wonder. We are not able to send them a message they will ever receive, but we can do what we are doing now. We can lie awake. We can think of them. We can hold them, whoever they are or are not, in the small, warm space of our attention for a little while before sleep. That is something. That is something. A single light in a window, far away. Before we go further, I want to return to a single equation. Not because equations matter more than silence, but because this particular equation is one of the few honest ways of looking at your own uncertainty. It does not prove anything. It simply helps you see, very precisely, where you do not know. It was written by the same astronomer I mentioned earlier, Frank Drake, the one who sat in Green Bank in 1960 and listened to Tau Ceti and Epsilon Eridani and heard nothing. A year after that, in 1961, he convened a small meeting at the same observatory. 11 people in a small room. Among them was a young Carl Sagan, still in his 20s.
Also present was a biochemist named Melvin Calvin, who learned during the meeting itself that he had just won the Nobel Prize in Chemistry. Drake needed an agenda for the discussion. He wrote one on the blackboard. What he wrote has since become known as the Drake equation, though Drake himself was never comfortable with the name. He considered it less an equation than a way of organizing ignorance. The equation is simple. It multiplies together a series of probabilities to estimate how many technological civilizations capable of radio communication might exist in our galaxy. The rate at which stars suitable for life are formed, the fraction of those stars with planets, the fraction of planets that are habitable, the fraction of habitable planets on which life actually arises, the fraction of living worlds on which life becomes intelligent, the fraction of intelligent species that develop technology, and, the last and heaviest term, the average length of time a technological civilization persists. That is all. You may notice that the equation does not give an answer. It gives a place for an answer. Each term is a window into our own uncertainty, and depending on what numbers you put into it, you can get a galaxy with millions of civilizations, or a galaxy with one, us. If you are honest, you have to admit that you do not know. None of the terms are known with much precision. The first, we know roughly, perhaps to within a factor of 2. The second we are beginning to know, thanks to Kepler and other surveys. The third, we know roughly. The fourth and fifth are guesses. The sixth is a guess inside a guess. And the seventh, the lifespan of a civilization, is, in essence, a question we are asking about ourselves. Here is what I find remarkable. If civilizations typically lasted 10 million years, the galaxy would be full. If they typically lasted 10,000 years, it would be empty.
The difference between those two numbers is the difference between a loud sky and a quiet one. And we, at this moment in our own history, do not know which of those numbers resembles us. Our own technological civilization, measured from the first radio transmission, is roughly 130 years old. We are not yet a civilization by the equation's standards. We are an embryo. This, I think, is one of the most important things the Drake equation does to us. It translates Fermi's question from an astronomical one into an intimate one. It says, if you want to know why the sky is silent, look at yourself, at how long the thing you are can possibly last, because your own duration is the final term. It is the one variable, in principle, that you can influence. And so, when I look at the equation, I do not think about stars. I think about us, about the long, slow, unfinished experiment we are inside of, about the question we are asking the galaxy, which is also the question the galaxy, through us, is asking back. Now I want to tell you about a star that behaves strangely. Its catalog name is KIC 8462852. It has another name, an unofficial one, Tabby's star, after the astronomer Tabitha Boyajian, who published the first study of it in 2015. It is an ordinary-looking star in the constellation Cygnus, about 1,400 light-years away. Ordinary mass, ordinary age, ordinary color. But its light, measured by the Kepler Space Telescope over several years, does not behave the way the light of an ordinary star should. A normal star shines steadily. When a planet passes in front of it, what astronomers call a transit, its light dips by a tiny fraction of a percent, very briefly, with predictable regularity. It is like a small shadow passing across a face. The brightness returns. The planet swings around to the other side. A month, or a year, or a decade later, the shadow returns at the same time with the same depth.
Tabby's star does not behave like this. Its light dips, sometimes by 2%, sometimes by more than 20%, at unpredictable times, for varying durations, in shapes that do not match any planetary transit we have ever seen. Some dips are sharp, some are gradual, some are asymmetrical. The brightness returns differently than it fell, as if something is passing in front of the star that does not have a circular silhouette, something of strange, irregular shape, and whatever it is, it does not have a planet's regularity. When the data first became public, a few astronomers, cautiously, in a paper not intended for wide circulation, mentioned that one possible explanation, among others, was an artificial structure, a large engineered object built around the star to collect its energy. The kind of thing that in the literature on the search for extraterrestrial intelligence is called a Dyson sphere, after the physicist Freeman Dyson, who proposed in 1960 that a sufficiently advanced civilization might surround its star with collectors to harvest most of its radiation. Boyajian's paper did not claim this was a Dyson sphere. It listed possibilities: a dust cloud, a family of comets, a catastrophic collision, an artificial structure, and at the end, an unknown natural phenomenon we had not yet thought of. What happened next was instructive. Follow-up observations at various wavelengths produced more data. Infrared measurements, which would have detected the heat of any solid structure around the star, showed nothing. Ultraviolet data showed that the star has been gradually dimming over the past century, a fact inconsistent with a solid artificial structure, but consistent with a cloud of dust on an elliptical orbit. Radio observations, carried out at Green Bank, found no artificial signals. Most astronomers now believe that the most likely explanation is some form of circumstellar dust, possibly the remains of a recent, catastrophic event in the system. Perhaps a shattered comet, perhaps a collision of planetary debris. Not a civilization, just dust. I mention this not because it was almost contact. It was not. It was almost an artifact. Tabby's star is a good example of how science works when something looks strange. First, cautious wonder. Then verification. Then more data. Then, usually, a boring explanation. Not because boring explanations are inherently more true,
because boring explanations are consistent with the rest of what we know, and strange ones usually are not. But there is another reason I mention it. For a brief period, over a few months in late 2015 and into 2016, a group of people, astronomers and amateurs, journalists and writers, seriously considered the possibility that the sky had finally spoken. And when it turned out that the sky had not spoken, nobody was upset. Nobody said, "What a disappointment." Everyone shrugged, took a few more notes, and went back to work. That tells you something, I think, about us, about our capacity for silence. We are not in despair. We are not inclined to despair. We simply keep listening. There is a strange patience in the scientific community about this question, which I find quietly moving, as if there were a tacit agreement that the answer will come when it comes, and that not hearing it today does not mean not hearing it ever. Science is, among other things, a way of being well alone. Let me tell you about another object. You may have heard of this one. In October of 2017, the Pan-STARRS telescope in Hawaii detected a small, fast-moving object crossing our solar system on a trajectory that clearly showed it had not come from here. Its speed relative to the Sun was too high.
Its orbit was not elliptical, the way the orbits of comets and asteroids belonging to our system are elliptical. It was not bound to the Sun. It was simply passing through. It was the first confirmed interstellar object ever observed in our solar system. It was given a Hawaiian name, Oumuamua. The word can be translated roughly as a scout or a messenger from the distant past. Oumuamua was strange. Not in its behavior. Its trajectory was entirely consistent with physics. Strange in its shape. Analysis of the variations in its brightness suggested that the object was highly elongated, perhaps 10 times longer than it was wide. That is unusual. Most asteroids and comets are more or less round because gravity and time make them that way. Oumuamua was more like a cigar, or a thin pancake, or something stranger still. It was also accelerating slightly as it left the solar system. The acceleration was small but measurable, and it could not be entirely explained by the Sun's gravity. Usually, when an object in our solar system accelerates in this way, the cause is outgassing, vapor released from its surface, as with a comet. But Oumuamua had no visible tail, no dust, no obvious source of thrust. Some scientists, in particular the Harvard astronomer Avi Loeb, have suggested that Oumuamua might not have been natural at all, that it might have been something like a solar sail produced by a distant civilization drifting through interstellar space. Its shape, its acceleration, its lack of a tail, all of these, Loeb argued, are at least consistent with such a hypothesis, and therefore it deserves to be taken seriously. Most astronomers have disagreed. They have proposed other explanations, that Oumuamua was a fragment of hydrogen ice, outgassing invisibly, that it was a chunk of a shattered exoplanet, that its shape was atypical but not unprecedented. The scientific consensus, broadly, treats Oumuamua as natural, if unusual.
I will not take a side in this debate. It is not my job, and it is not the job of this channel. But I will note something that struck me about the case. Oumuamua was discovered a full day after it had already passed its closest point to the Sun. It was already on its way out when we saw it. We did not have time to send a probe. We did not have time to organize detailed observations. It flew through our system, gave us a few weeks of data, and was gone. If it was natural, it was a missed opportunity to study the first interstellar fragment ever to visit us.
If it was artificial, it was a missed opportunity of another kind. Either way, by the time we fully understood what we had, we no longer had it. This, too, I think, is part of the silence. Not that we do not see, that we do not see in time, that the galaxy, in its slowness and its vastness, sometimes passes close enough to us to be noticed and too quickly to be understood. Let us stay with Dyson spheres a little longer, because I mentioned them earlier, and they deserve more than one sentence. Freeman Dyson's idea, in its 1960 form, was simple. If a civilization continues to grow in its energy needs, and throughout the history of our own civilization, it has done exactly that, it will eventually run into a limit. The amount of energy that can be collected from the surface of a single planet is finite. The amount of energy emitted by a star is many billions of times greater. So, if a civilization wishes to keep growing, at some point, it makes sense to begin harvesting not just the light that falls on its planet, but the light its star throws into empty space. For that, you need a structure. Or rather, many structures. A swarm of collectors orbiting the star at different distances, oriented in different ways, absorbing the light and converting it into usable work. Dyson called it a sphere, though he himself noted that a solid sphere would be mechanically unstable. In practice, it would be a swarm,
Or a shell. Or something in between. And here is what matters astronomically. A Dyson swarm, or anything approximating one, would leave an observational signature. A star surrounded by such collectors would emit less visible light than it ought to, because the visible light would be absorbed. But it would emit more infrared, because the collectors, absorbing the light, would warm up and re-radiate the energy as heat. An astronomer scanning the sky in infrared would see a star with an excess of warmth relative to its visible brightness. It would be strange. It would be suspicious. It would be, in principle, detectable. A number of astronomers over the past decades have carried out exactly that kind of search. Richard Kerrigan, working at Fermilab, published the results of a search for Dyson sphere candidates in data from the IRAS infrared survey in 2009. He found a small number of sources that would merit further study, but none that held up as convincing. In 2015, the Glimpsing Heat from Alien Technologies project, led by Jason Wright at Penn State, looked not at stars, but at galaxies, about 100,000 of them, searching for the signature of a civilization that had colonized an entire galaxy and was using a large fraction of its stellar output. The idea was that a sufficiently advanced civilization might, over enough time, build collectors around a significant fraction of its home galaxy's stars, and the galaxy as a whole would emit anomalously much infrared compared to visible light. They found nothing. Not a single galaxy with that signature. 100,000 galaxies examined, and in every one of them, the radiation behaved as it should have behaved if no megastructures were present. This is, in my view, one of the underappreciated results of modern astronomy. We have not just been listening to our own galaxy. We have been looking at 100,000 others, searching for signs that any of them has been transformed by intelligence. We saw nothing. What does that mean? It means that if civilizations capable of building galaxy-scale megastructures exist, they are either not in those 100,000, or they have chosen not to build such things, or they exist in forms we have not yet learned to recognize. Any of these is important knowledge. Any of them narrows the space of possibilities. That is, in a way, one of the few positive things you can say about the silence. It is informative. Every place we have looked and not found a civilization narrows the map of where they might still be.
The hour, I can feel, is moving now. Not toward dawn, toward that quiet middle stretch of the night where time seems to pause a little. If you are still with me, I am glad you are here. We are not finished. There are a few more things I want to walk you through. I want to come back to the James Webb Space Telescope because what it is doing is something genuinely new, and I do not think I gave it a fair account earlier. The telescope was launched on Christmas morning, 2021. I remember that morning. I watched the stream from home. The launch had been postponed so many times over the previous years that it had started to feel as if it would never actually happen, as if the telescope would remain forever in its clean room in French Guiana. Too expensive, too fragile, too symbolic for anyone to dare send up. But on that morning, it was sent. The rocket rose cleanly. Within hours, the telescope had separated, deployed its solar panels, and begun its long journey to the second Lagrange point, 1.5 million kilometers from Earth. That is where it is now. It moves in a small orbit around that point, always turned toward the sun on its sunshield side, always facing outward into the dark.
Its primary mirror is 6.5 meters across, composed of 18 hexagonal segments, coated in a thin layer of gold because gold reflects infrared light well. It is the largest optical mirror ever launched into space, and it was designed specifically to see in the infrared, the same band of light in which, as I mentioned, a Dyson swarm would shine more brightly than it should. But Webb was not built to search for Dyson spheres. It was built, among many other things, to do one very specific thing that had never been done before, at least not at this sensitivity: to analyze the atmospheres of distant planets. The method is called transmission spectroscopy. It works like this. When a planet passes in front of its star, a tiny fraction of the star's light travels through the atmosphere of the planet, not through its dense core, but through the thin ring of gas at its edge. Different molecules in the atmosphere absorb different wavelengths of light. Water vapor absorbs one set of wavelengths. Carbon dioxide absorbs another. Methane another still. If your spectrometer is sensitive enough, you can break apart the starlight that has passed through a planet's atmosphere and read what molecules are there, as if the atmosphere were a kind of signature the light had left in the margin of a page. Before Webb, we could do this only for certain gas giants, very close and very large objects. With Webb, we are beginning to do it for smaller planets, for rocky worlds, for planets that might, in principle, host liquid water. And here is what we are looking for. Not intelligence. Intelligence is too faint a signature to be found this way. We are looking for biospheres. We are looking for chemical combinations that are hard to explain without living processes. Oxygen, for example. Free oxygen in an atmosphere is an unusual thing. Oxygen is highly reactive. It wants to combine with other things.
On a planet without living processes constantly producing oxygen, it disappears from the atmosphere within a few million years, bound up in rocks, in iron, in carbon. The fact that Earth's atmosphere is roughly 21% oxygen is a consequence of billions of years of photosynthesis. Without plants, without algae, without cyanobacteria, Earth's oxygen would be gone. So if Webb finds a rocky planet with an oxygen-rich atmosphere, it will be telling us a great deal. Not that there is a civilization there, not that there are animals, simply that there is, probably, something alive, something continually producing oxygen against chemistry's tendency to remove it. We have not found anything like that yet. I should be honest. As of this moment in history, the atmospheres that Webb has analyzed so far do not show convincing biosignatures.
Some have shown water vapor. Some have shown carbon dioxide. One, recently, showed a tentative signal of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by marine microorganisms. But the measurement remains contested, and most astronomers regard it with caution, waiting for confirmation. I mention this not to say that we have found something. We have not. I mention it to say that we are, for the first time in the history of our species, in a position where we might find something. That the instruments which would see life on another planet, if the life is there in sufficient quantity, are now operating, aimed, collecting data. The answer, whatever it turns out to be, is beginning to be possible. This is new. No previous generation could have done this. Our grandparents lived their whole lives not knowing whether planets even existed around other stars. The first confirmed exoplanet was only announced in 1995. Our parents lived most of their lives not knowing whether such planets were common. The surveys showing they were common arrived only with Kepler in 2009.
And here we are, the generation that will first be able to look at the atmosphere of a planet the size of Earth and ask, is there anything there that breathes? Perhaps the answer will be no. Perhaps we will look at 1,000 such atmospheres and all of them will be sterile. That too would be knowledge. That too would narrow the map. But perhaps one day, and this is a possibility we may have to learn to live with, perhaps one of those atmospheres will show a signature that is hard to explain otherwise. And then we will find ourselves in a strange position, knowing that somewhere out there, 100 light years away, a planet is breathing, and having no hope, at least none with our present technology, of ever going there. Knowing about an alien life and never meeting it. I am not sure how we will take that news. Perhaps well. Perhaps it will be one of the quietest discoveries in the history of science, precisely because it will come slowly, through spectral lines, through papers, through years of confirmation, and not through a signal in the night. Perhaps by the time we are sure, we will long since have made peace with it. Meanwhile, the telescope watches. Each image takes hours of exposure. The field of view slowly accumulates light. The data is transmitted back to Earth. Astronomers analyze it. They write papers. They go through peer review. They publish. Someone, in some university library or at home in the middle of the night, reads the paper and for the first time understands something about a world that was unknown to us a month ago. This, too, is a kind of silence, a patient, careful, attentive silence. I find that I like it. Now I want to talk about deep time, because the part of the paradox that is hardest to hold in mind, I think, is not its spatial scale, but its temporal one. We are not good at feeling time. We understand days, we understand years, we understand, with some effort, generations.
But beyond a few thousand years, our internal sense of time gives out. We begin to operate with numbers instead of sensations. 1,000,000 years, 10 million, 1,000,000,000. These become just words. They sound similar. They feel intuitively about the same. They are not the same. The difference between 1,000,000 and 1,000,000,000 is a factor of 1,000. but our minds barely distinguish them. Let me try to give you an image that sometimes helps. Imagine a year as a single meter. A whole human life, from birth to death, becomes a stretch of about 80 meters, the length of a city block. The entire history of human civilization, from the first settlements in the Fertile Crescent to now, becomes about 10,000 meters, or 10 kilometers. You could walk it in a couple of hours at a brisk pace. Roughly the distance between two metro stations. Our biological species, Homo sapiens, is about 300,000 years old. That is 300 kilometers, already a journey. The distance between two large cities. But the planet we live on is 4.5 billion years old. That is 4.5 million kilometers, about 11 times farther than from the Earth to the Moon. No longer a walk, no longer even a journey. Something that has to be imagined as a space voyage. And the galaxy is 13.5 billion years old. That is 13.5 million kilometers, about a tenth of the distance from the Earth to the Sun. Almost unimaginable. And in that length, in that enormous length of time, humanity is the last 300 kilometers. Civilization is the last 10. Radio is the last 100 meters. Our own search for extraterrestrial intelligence is the last 66 meters. Think about that. The whole history of our listening is a hallway the length of a room. A small hallway at the end of a very long road. When you hold that in mind, the absence of a signal stops being shocking. It becomes almost expected.
We have been listening for the equivalent of a single breath in a conversation that lasts thousands of hours. If no one is speaking in this precise second, it does not mean there is no one. It means that we arrived late, and our own attention has been very brief. Here is another way to think about it. The stars we see at night are not shining with the light they are producing now. They are shining with light they produced centuries or millennia ago. The light from Sirius, one of the brightest stars in our sky, is about 8.5 years old. When you look at it, you are looking into the past. The light from the stars of Orion is hundreds or even thousands of years old. When you look at Orion's belt, you are seeing light that was emitted at different times in different epochs of human history. And that is only now, tonight, this moment, reaching your retina. This means the sky we see is not a map. It is an echo. We are looking at a composition of moments, each of which was present in its own time, now assembled with other moments into something we call the night sky. The stars in our sky do not exist simultaneously, in the sense in which we see them. Some of them may no longer exist at all. Some of them may have exploded as supernovae thousands of years ago, and the light of that explosion has not yet reached us. When it does, we will see a star flare brilliantly and vanish. But by the star's own clock, it vanished long ago. The silence we hear from the galaxy is an echo, too. If somewhere, 50,000 light-years away, on the other side of our own galaxy, a civilization sent a signal, say, in the time of ancient Egypt, that signal will not reach us for another 35,000 years. And if a civilization sent a signal 50,000 years ago, and that signal is now passing through Earth, we would hear it, provided we were tuned correctly. But its sender has almost certainly been gone for a very long time.
Their descendants, if there are any,
Have forgotten the signal was sent. They may not even know their species once sent such things. So when we ask, where is everybody? We are really asking, where was everybody thousands or millions of years ago, with such precision that the light of their signal would cross exactly the right amount of space to arrive here exactly now? That is perhaps the most demanding of all questions, and the least likely. It is no wonder the answer has not yet come. Now about stranger time, about the future. Our sun, as I mentioned before, has about 5 billion years left before it begins to expand into a red giant. That is a long time. Longer than the whole evolutionary history of life on Earth to this point. If humanity has any chance of persisting, even in some modified, unrecognizable form, we have ahead of us roughly as much time as all of biology has had behind us, from the first bacteria to now. But the sun is not the only clock. The universe has clocks of its own, and they run on much larger scales. In about 100 trillion years, the last of the long-lived red dwarf stars, stars far dimmer and more economical than our sun, will stop shining. After that, there will be no new starlight in the observable universe. There will be black holes. There will be the cooling remains of dead stars, white dwarfs slowly becoming black, neutron stars slowly losing their heat. There will be thin gas distributed across vast spaces. There will be, very gradually, a great deal of silence. This phase is called the degenerate era. It is not a catastrophe. It is simply a long cooling. The universe will run out of the fuel it needs to make new light, and everything that remains will be the slow dimming of what already exists. And even that is not the end.
In roughly 10 to the 100th years, a number so large that writing it in digits is meaningless, even black holes will evaporate through a process predicted by Stephen Hawking, losing mass as faint thermal radiation. After that, if current physics is right, the universe will contain nothing that can really be called structure. Only low-energy photons, extremely rarefied, drifting in an ever-expanding space. This is called the heat death. It is a hypothesis, not a prediction. It is a possible final fate for the universe based on what we currently know about its expansion and about the second law of thermodynamics. It may be wrong. Perhaps the universe is cyclical. Perhaps there are processes we do not yet understand. But based on the data we have, this is the most likely direction. And here is a question I sometimes think about at night. If the universe does end this way, slowly cooling into nothing, then every civilization that has ever existed will eventually have to face this fact. Not that it will itself die, that part we understand, but that even the longest efforts to preserve memory, meaning, culture will, in the end, dissolve. That the last computer, the last photon of information, the last trace of anything that ever existed will all, one day, be thermal noise in rarefied gas, expanding in the dark. This ought to be depressing. For me, somehow, it is not. Perhaps because the scales are so vast that they become abstract rather than personal. Perhaps because everything that has existed has existed. That fact does not depend on whether someone later remembers it. The existence of a thing is its own fact. It does not need an observer in the far future to be true. I do not know if everyone feels this way. I only know that when I think long enough about it, about everything we do eventually disappearing, I do not find it frightening. I find it freeing.
As if it is permission to live a small life, do small things, love a small number of people, and not worry about leaving something large behind. Because no one is going to leave anything large behind. That is not a defeat. It is simply the condition under which we are allowed to exist. That, I think, is what a certain astronomer meant when he said that cosmology is, above all, a school of humility. Not because it makes us feel small, because it frees us from the obligation to be large. There is one more thing about the silence that I want to say, and this is, perhaps, the strangest part of the paradox, but it is also the part that brings me the most peace. We do not know why the silence exists. We have drawn up a list of possible causes. We have ruled out a few of them. We have not ruled out most of them, and perhaps we never will. Perhaps the correct answer is something we have not yet thought of. Some feature of the cosmos, or of life, that our species is not yet mature enough to understand. That is all right, because living with the incomprehensible is, in the end, what consciousness is for. Not to resolve, not to close, to hold. To stand in front of something you cannot explain and keep paying attention. There is a discipline in that. There is a form of dignity in that. To not demand an answer, to not take offense at its absence, to keep looking, keep listening, keep being here. That perhaps is what we are doing as a species. At the collective level, through our telescopes and our astronomers, through our probes and our decades of searching, we are learning to stand in front of the silence and not leave. It is a small achievement on galactic scales, but it is ours, and it may matter more than any answer we could receive. Let me come back now to something closer, more human, because I have spent a lot of time at the galactic scale, and I think this is the right moment to come back down. There is a thought I return to often, and it does not fit neatly into any of the hypotheses I have described. It is not really a hypothesis, it is an observation. Here it is. If an alien civilization genuinely wanted to reach us, not our governments, not our scientific community, but us as individual people, we might not be able to recognize the attempt, even if it were in front of us. Consider this. Our way of communicating with each other is speech and writing and everything that has grown out of them. We divide reality into separate sounds, separate words, separate sentences. We assume that communication is a sequence of discrete units that get decoded one after another. That is our solution to the problem of transmitting information. It is not the only solution. Dolphins, for example, produce broadband clicks and whistles that, according to recent research, may carry far more information per second than human speech. Bees communicate by dancing, geometric figures that encode the distance and direction of flowers. Octopuses may communicate through color, changing the pigmentation of their skin in rhythms and patterns we are only beginning to analyze. These modes of communication exist on our own planet, and even with them, with creatures that share our biochemistry and our evolutionary history, we struggle to understand what they are saying, if they are saying anything at all. Now imagine a civilization that emerged on a planet around another star, from a different chemistry, under a different gravity, with a different sensory configuration. Perhaps it sees in the radio band. Perhaps it hears magnetic fields. Perhaps it communicates through modulations of electric potential, or chemical plumes, or variations in gas density. Perhaps its time runs slower than ours, or faster, or not monotonically at all. Perhaps it thinks not in words and not in images, but in something for which we have no name.
If such a civilization tried to say something to us, what is the probability that we would notice? That we would tune our instruments to the right channel, at the right speed, with the right grammar? Very small, perhaps zero, and that is not because we are stupid. It is because communication is, in a deep sense, an assumption about a shared world. It assumes that two parties have enough sensory, temporal, and conceptual common ground that one can hope to be understood by the other. Between species on the same planet, that ground is thin. Between species on different planets, it may be absent altogether. So perhaps the silence is not silence. Perhaps it is a polyphony we are not tuned to hear. The sky, on this view, may be full of conversations. The conversations simply happen at speeds, in channels, and in codes that, to us, look like the background noise of the universe. We would be, in that picture,
not lonely listeners. We would be listeners who have not yet learned to distinguish language from wind. I do not know if this is true, no one does. But I find the possibility strangely consoling. It does not promise that we will find anything soon, but it reminds us that the absence of understanding is not the same as the absence of speakers. It is only an acknowledgement that we are at an early stage of what we might one day become. I like that thought. That we may not be deaf, that we may simply be children who have not yet learned to hear. Now let me tell you about a simpler thing, about molecules. One of the most remarkable things astrochemistry has discovered over the past half-century is how much life seems to have been prepared for in advance. I mean this. When we look at the clouds of gas between the stars, at cosmic nebulae, at the protoplanetary disks around forming stars, we find molecules there. And these molecules are not random. They are, increasingly, the very molecules that life on Earth is built out of.
Amino acids, the building blocks of proteins, have been found in meteorites, most famously in the Murchison meteorite, which fell in Australia in 1969. Sugars, including ribose, one of the key components of RNA, have been identified in other meteorites. Complex organic molecules, including precursors to the nucleic acids, have been found in interstellar gas clouds and in the tails of comets, and on the surfaces of icy moons in our own solar system. What does that mean? It means that the chemistry we are made of is not unique to Earth. Its fragments, its precursors, its necessary bricks are scattered across the galaxy. They do not require a planet. They do not require an ocean. They form in vacuum, in the icy mantles of dust grains, in the plasma discharges around young stars. By the time a planet assembles itself out of that dust, it already inherits most of what it needs to begin. This shifts the weight of the paradox. The old picture, in which life arises only on very rare, very finely tuned planets, from very simple chemical ingredients through a very improbable sequence of accidents, becomes harder to defend. The ingredients are not rare. The ingredients are everywhere. If anything is rare, it is not the raw material, but the recipe. And even about the recipe, we have reasons to think it is not too complicated, because life on Earth found it almost immediately. This, in turn, deepens the paradox. Because if the chemistry of life is easy, and its ingredients are everywhere, then the filter, if there is one, must be somewhere later. Perhaps at the step from simple life to complex. Perhaps at the step from complex life to intelligent. Perhaps at the step from intelligent to technological. Perhaps at the step from technological to enduring. Somewhere on that ladder, there is a rung that breaks, and we do not know which. I sometimes think of us as a small experiment on that ladder.
We are one of the cases in which biology has actually made it to a step where it can be observed from the outside. We are one result of a universe that has, perhaps, run billions of other experiments, most of which did not reach our rung. We do not know if this is ordinary or rare. We do not know if it is normal or strange. We only know that it happened here, once, with us. And perhaps one of the gentlest things we can do with ourselves is not to draw conclusions too soon. Not to call ourselves unique or typical. Not to decide whether we are exceptional or ordinary. Simply to be what we are and to keep watching. One more small thing I wanted to say about our own transmissions. It is often imagined that Earth is broadcasting loudly into space, that our radio, our television signals, our radar pulses are spreading outward in every direction as a vast sphere of electromagnetic noise, announcing our existence to any civilization within a few dozen light years. It is a romantic picture. It is also, for the most part, incorrect. The problem is that our transmissions are very weak. They fall off with the square of the distance.
By the time the earliest radio broadcasts, sent out in the 1920s and 30s, reached a nearby star, their intensity had dropped to a level that, by the calculations of the engineers who study this, could not now be distinguished from background noise even by our best receivers. And today, as most transmission has moved to cable, to satellite relay, to direct fiber, Earth is in a sense becoming quieter in the radio band, not louder. We speak increasingly through directed beams, not through broadband shouting. A casual alien observer scanning our sky today would see less than they would have seen 30 years ago. This consoles me somewhat, not because I think we ought to be hiding, but because the romantic picture of Earth shouting into the dark overstates our own voice. We are whispering, not shouting.
And whispers are hard to hear even close by. There have been experiments, though, in which we shouted on purpose. In 1974, to celebrate an upgrade to the Arecibo radio telescope in Puerto Rico, Frank Drake and Carl Sagan designed a short message and sent it toward the globular cluster M13 in the constellation Hercules, some 25,000 light-years away. The message contained numbers, atomic formulas, a simple diagram of a human body, and a schematic of the solar system and the radio telescope that sent it. It will reach M13 in about 24,900 years. By that time, if anyone receives it, the Earth, if it still exists as a civilization, will be something altogether different. There is something melancholy about a gesture like that, sending a bottle into the ocean, knowing that you yourself will never learn what became of it, that the answer, if it comes, will come 50,000 years from now, 25 there, 25 back. By then, no one we know, none of our children, none of our children's children, no one we could call ours, will be there to receive it. But the gesture was made, the bottle was thrown, and perhaps that is the whole point. Not the answer, the gesture, the act of speaking itself, the declaration that we were here, that we thought, that we wanted to be heard. That, it seems to me, is what makes us a civilization. Not our discoveries and not our achievements. The fact that, knowing we will never see a reply, we still send the message. The hour continues. The house, I can hear, has gone fully still. Even the radiators have stopped knocking. This is the part of the night that belongs to those who are not asleep, to those who are reading or working or simply lying awake, thinking. To those who become, for these few hours, the only witnesses to the fact that the universe is still going on. There is something I want to tell you, a small thing that struck me once.
In 1990, when the Voyager 1 spacecraft was about 6 billion kilometers from Earth, on its way toward what is now its endless drift, Carl Sagan convinced the mission team to turn the camera around and take a photograph of Earth. Not for any scientific reason, simply to see. The photograph came back. On it, Earth is a single, tiny, pale blue dot, less than a pixel in size, floating in a beam of scattered sunlight that happens to cross the frame. Around it, black. No context, no sign that this particular dot is in any way different from any other dot in the image. Just a small blue grain in a wide emptiness. Sagan wrote about that image in a small book. He pointed out that on that dot, the whole of human history has taken place. Every war, every love, every invention, every religion, every child who was ever born, every old person who ever died. All of it happened on that tiny, pale blue fleck, barely visible from a distance that, on galactic scales, is not really a distance at all.
Voyager, at that moment, was not far. It was just a little beyond Pluto, and already, at that distance, Earth looked like this. Now step farther, in your mind. Step away a light year. 10. 100. The sun becomes one star among others, no longer especially bright, nothing to distinguish it. From a few thousand light years, our sun is no longer even visible without instruments. It disappears into the background of the galaxy. And Earth? Earth has long since been invisible. It does not exist from the perspective of any observer beyond our immediate solar neighborhood. It is there, but it cannot be resolved. It dissolves into the general light of its star, the way a drop of water dissolves into an ocean. That, I think, is an answer to a question people sometimes ask about the paradox. If we really mattered on a galactic scale, wouldn't some civilization have noticed us? The answer is, no, they would not have. Not because we do not matter to ourselves,
but because, from a galactic distance, we are physically invisible. There is no way, with any current technology, to resolve our planet against the brightness of the sun from more than a few dozen light years away. We are, in every sense, absent from the galactic map. And this, by a certain irony, means that if we are not being looked for specifically, we will not be found. Even if the galaxy is full of civilizations, most of them may, simply by virtue of distance, not know that we exist. Not because they are uninterested, because their instruments, like ours, have limits. They see their immediate neighbors. Beyond that, they have the same vague intuitions about possible life that we do. We may all be like this, each of us on our own small planet, looking at our own small sky, knowing about a few nearby stars, and knowing nothing about the rest. Each of us alone to the same degree as all the others. Not for lack of companions, because of a shared condition. That is, in a strange way, a little easier to bear. To know that our isolation is not special, that if there are others, they probably feel the same way. We may all be pondering our common situation, each of us in our own language, each of us at our own pace, and none of us reaching each other because the distances are simply too great. A shared loneliness, distributed across the void, but not divisible within it. There is, I think, something tender in that thought. If we could send a message that really arrived, perhaps it would be, "We hear your silence, and we understand. We too are silent. We too are watching. We too are trying." But such a message will not arrive, not because it is not worth sending, because it has, in some sense, already always been sent. The simple existence of thinking beings, wherever they are, is in itself a form of signal. The fact of attention, wherever it arises, is a small transmission upward. Not in a form a radio telescope could detect,
but in a form that may be part of the fabric of what it means to be a universe that has, through its local expressions, begun to turn around and look at itself. I know that is speculative. I am not defending it as a theory. I am offering it as a way of seeing, as a night thought, as the kind of thing that can accompany you into sleep without needing to be true in any technical sense. Because in the end, these are the thoughts the late hours are for. Not for conclusions, not for proofs, for a certain kind of breathing that happens in the mind when it is allowed to move slowly and without hurry. The Fermi paradox is not a math problem to be solved before sleep. It is a room you can sit in for a while, and when you have sat in it long enough, it stops frightening you. It becomes a place where the universe behaves a little strangely, and where we, being part of it, behave a little strangely too, because we are the part of it that is thinking about it. I am almost finished. Let me leave you with one last image, the one I have returned to before, and which seems right to return to once more here. Imagine a window, far away, very far, so far that you cannot even be sure whether it is really there or whether it only seems to you that it is. In that window, a light is on. Maybe someone lives there, maybe not. Maybe the light has been left on by accident and no one is in the room behind it. You will never know. The window is too far to know. But the light is there, and you can see it. And seeing it, you become for that brief moment connected to it. Not in any practical sense, not in the sense that anything could be sent or received, but in the simple sense that two sources of light, wherever they are, exist somehow in the same universe, and each, in principle, could see the other, if they looked at the right time, in the right direction. That is not much, but it is not nothing. You are one of the lights. Somewhere, perhaps, there are others. We may never meet,
But we are here. And that, in the end, is what there is. The fact of presence. The fact that someone is looking. The fact that in a universe which could have been entirely silent in every way, there is at least one point at which something is paying attention. Perhaps there are other such points. Perhaps each of them feels alone. Perhaps loneliness is the common currency of consciousness wherever it arises. Perhaps in the whole galaxy, at any given moment, there are many beings lying awake, thinking about distances, and each of them is thinking that it is the only one. If that is so, then we are not alone in our solitude. We are alone together. And that too, I think, is a form of communication. Inaudible, unprovable, but perhaps real. Let the silence not frighten you. It is not against you. It is simply the condition we find ourselves in, and perhaps many others have found themselves in as well. It is not a verdict. It is a context. And now let me step back. The hour is very late, and you may be near sleep. Let sleep come gently, if it comes. Let these thoughts leave the mind when they are ready to. They do not require a solution. They do not require an answer. They have simply been, for these few hours, your company in the dark. Somewhere, very far away perhaps, there is a window. In it, a light is on. Someone, perhaps, is watching. Or perhaps not. The silence continues. And that is all right.